While quadratics are often the type of polynomial we are most familiar with, there are many other types of polynomials out there. In fact, there's infinitely many other types of polynomials out there. And today is going to be really talking about what are these other types of polynomials, what are their characteristics, and why do we care about them. So, as always, feel free to jump to a particular point of this video that you may be most interested in by using the timestamps included in the video. And without further ado, let's go ahead and get started. So power function is any function that has an x raised to some power, where this power is any real number, and it's maybe being multiplied out front by any real number. And we're going to talk about these because the behavior of these power functions really is very telling about the behavior of polynomials in general. But before we dive too deep into that, we want to make sure that we can identify who is and isn't a power function, because sometimes it's not immediately obvious. For example, if I have a 2 here, he's actually secretly multiplied by an x to what power? In particular, 2 is the same thing as 2 times 1, and x to what power gives me 1? That would be x to the 0th power, and 0 is a real number, so that is indeed considered a power function. What about here? If I have a plain x, what's secretly his exponent? That's a 1, so I have an x in the base, a real number in the exponent, I'm good. Here if I have x squared, even though that's a quadratic, that's also considered a power function. If I have 1/4 times x to the cubed, again we have an x in the base and a real number being multiplied by out front, in this case 1/4, so that's also considered a power function. What's wrong with this last function? That's an exponential function. We have a 2 in the base and an x and an exponent. That is not considered a power function. That's exponential functions. We've already studied those. That is not what we're dealing with today. And in particular, power functions have very predictable behaviors whenever we're dealing with any integers inside those exponents. So let's take a look at this. If we have things like x squared, x to the 4th, and x to the 6th, they all take this same general U shape. Well, if I have things like x to the 3rd, x to the 5th, x to the 7th, they all take this same general S shape, as you will. So in general, this is the general behavior, the general end behavior, when all of these exponents are even integers. And that's actually a very powerful idea, with even just x squared being the most basic that looks like that. While this is the general end behavior whenever those exponents are odd integers. Of course, if we have just x to the 1st, that's a straight line, but as soon as we get something bigger than the 1st, such as cube, 5th, and 7th, it becomes a little bit more squiggly there in the middle. But the end behavior is still the same. Oh, excuse me. All right, so whenever we're talking about power functions, this is a really nice idea to fall back on. So if we have an even power, even integer power, it's going to be an upward shaping U. And if the number out front is positive, it's going to be stretched somehow, but it's still going to be an upward shaping U. If it's negative, that'll be downward shaped. It'll be an upside down U. If he's odd and positive, he's going to be this general positive curvy shape, this S shape, if you will. And I would remember that by the fact that that looks like a positive slope. That's sort of the idea, is it's still facing the same general direction as a positive slope. Versus if I reflect him over that x-axis with a negative number out front, he's going to end up having a negative slope. So over here, this would be something like x to the 4th. This would be something like negative 2x to the 6th. And this would be something like 3x to the 5th. And this would be something like negative 4x to the 7th. So notice I don't care if that number out front happens to be odd or even. What I care about is this number in the exponent. And that's again true whenever we have integers up here in the power function. So we can determine if it's even or odd, whether or not the number out front, that constant, is positive or negative. I should really relabel that as the coefficient. Although you can think of it as a constant because it's whatever is the number out front. It's not inside the exponent. And then you can use that to identify the end behavior. And I would always kind of keep in mind how x squared and x to the 3rd behave in order to sort of determine that overall end behavior. So let's just predict that. Go ahead and pause your video and see if you can sketch out and predict the end behavior of each of these functions. So this first one has an odd exponent, so it's an odd power, with a positive coefficient. So he's going to have an end behavior that looks like this. What about this next one? Well, he is also still an odd exponent, odd power, but now we have a negative coefficient. And that odd comes from that 7 up here. So he's going to be facing the other direction. This one now has an even exponent and a positive coefficient. So he's going to be a right side up u. Now we have an even exponent again, but this time the coefficient is negative. So he's going to be an upside down u. Whenever we add more things on than just having, one number times an x2 an integer, when we have more things added on, now we are dealing with a polynomial function. So a polynomial function has a few characteristics. So all of those exponents specifically have positive integers in them. And that's definitely not how you spell positive. Ooh. Positive integers in the exponents. And we only are dealing with x to an exponent whenever we're dealing with all. So it's basically like a whole bunch of power functions being added together, where specifically what's inside the exponent is a positive integer. Because power functions, technically by definition, it doesn't have to be an integer, but for polynomials it does. And we also have real numbers as those coefficients out front. Those can be positive or negative. They can also be non-integers, that's fine, but they're all real numbers out front. So both of these are like examples of polynomials. So there's kind of our really, really basic ones like quadratics, like x squared minus 1. You can also have kind of funkier ones like negative 4/3, x to the 7th plus x to the 3rd minus x plus square root of 3. It's okay that this 3 has a square root because that's just a plain old constant, a plain old number. What would not be okay is an x underneath the square root. And these have some particular characteristics. What's super nice about them is they are continuous and smooth. So they've always got these nice, beautiful, rounded curves. And that's going to be really helpful if you ever study some higher level math like calculus, that there's a lot of like nice properties that come out of that. So let's just practice identifying them visually. So here I've got 2 of these that are polynomials and 2 of them that are not. Go ahead and pause your video and see if you can predict which are and which are not. So this first one, that is a polynomial because he's continuous, he's smooth, it's nice and beautiful. This next one, this is also a polynomial because he's continuous and smooth and nice and beautiful. This one is not a polynomial. In particular, this is our problem. This sharp corner means he is not. In particular, this is actually an absolute value function, if you remember that. So that is not a polynomial. This one is also not a polynomial because he is not continuous. So even though he's smooth, because he's not continuous, he is not a polynomial. We can also identify polynomials from simply how they're written out. So this first one, he is a polynomial. Why is he? He's actually times x to the what? X to the 0 with power. So he actually counts. He's considered a polynomial. This next one, even though he's not quite simplified, is also considered a polynomial because he would simplify to 2 times 3 is 6, x cubed times x is x to the 4th, plus a 4. We're good. We're just dealing with x to an exponent, real coefficients. This guy, he's again not simplified, but even if you distributed him out, he would still be a polynomial. This next one is not a polynomial. What's the problem with that? Because of this square root, that would be the same thing as 5 times x plus 2 to the 1/2. And 1/2 is not an integer, or is not a positive integer specifically. A positive integer. So that is not a polynomial. What's the problem here? I have x's inside of the denominator. So in particular, this would be like x squared minus 3 times x to the 6 plus 7 all to the negative 1, and that is not a positive integer. In particular, this is called a rational function. We're going to study that a little bit later, but that's because we've got x's in the denominator, not a polynomial. When we're talking about how to describe polynomials, there's a few important things. Whatever is the highest power term tells you a lot about the behavior of the polynomial, so we end up having a lot of special words for that. That's the leading term, and that's true regardless if he's literally listed first or if I happen to reorder it where he was listed at the end. That would be not conventional, but that would still be considered the leading term because he's the highest power. Whatever is the number out front of the x is your leading coefficient. So in this case, that's negative 4/3. And the degree is whatever the highest power is. So when I'm talking about the degree of the polynomial, I actually don't care that there's like this x cubed minus x plus square root of 3. I just care about this very first term with its highest power. And that's because the overall behavior of the polynomial mostly follows what's going on with that highest power. So in order to identify all of these things, you really want to figure out what is the highest power of x, and then you're going to be able to talk about the leading term being that entire thing and the leading coefficient being the number out front of it. So let's go ahead and identify some of these. So go ahead and pause your video and see if you can identify the leading term, leading coefficient, and degree of all of these. So here, the highest power is this 5 times x to the 4th, so our leading term is the entirety of 5 times x to the 4th. The leading coefficient is the number out front, which in this case is 5, and the degree is that highest power, which in this case is 4. On this next one, it might have been tempting to call it x cubed, but be careful, that is not the highest power. The highest power is actually here, and that negative is attached, so the leading term is negative 2x to the 6th. That makes the leading coefficient negative 2, and the degree 6. Now let's just pause and notice some of the overall behavior of these. So just like even power functions had an end behavior of being a right side up u, if it was an even power with a positive coefficient, that happens for polynomials as well, even if there's something a little bit more interesting going on in the middle. Same thing here, where I now have an even power with a negative leading coefficient. That looks like an overall upside down u in terms of that end behavior, even if there's more interesting stuff going on in the middle. And in particular, the way that you might note that, to note that you understand that there's interesting stuff going on in the middle, is you might kind of draw it out like maybe there's some interesting stuff going on in the middle, but the overall end behavior looks like this. Go ahead and pause your video and see if you can identify the same thing about these polynomials. So here, the leading term is again that highest power, so it's positive 3x to the 5th. That makes the leading coefficient 3, and the highest degree 5. For this next one, he's already thankfully in order, so his leading term is negative 6x to the 3rd. That means the leading coefficient is negative 6, and the degree is 3. And this also follows similar behavior to those power functions, where if I have an odd leading term with a positive coefficient, overall follows this end behavior, but again with more interesting stuff perhaps going on in the middle, which I can sort of note. And then if I have an odd leading term with a negative coefficient, I again have that overall end behavior, even if there's some more interesting stuff going on in the middle. So we can identify the overall end behavior of a polynomial by identifying what is the leading term, and in particular what his degree is, and what is that leading coefficient, positive or negative. So go ahead and pause your video and see if, without the use of a graphing calculator, if you can predict the overall end behavior of each of these polynomials. So here I'm just going to box in that leading term. So because this leading term is even with a positive leading coefficient, his overall end behavior should look like this. It should be a right side up u. For this next one, the leading term is negative 6x to the 10th because that is the highest power. So he should be an upside down u with maybe some stuff going on in the middle. For this next one, the leading term is this 1/7 x to the 7th. So he should be a positive odd function. So he's going to be odd, so he's going to have opposite directions, and he's going to have an overall positive slope to him. This next one only has one term. He also happens to be a power function. He's a both polynomial and a power function. And he's going to be facing the other direction, but still odd. Odd because of this 103. And that in general is how those end behaviors look. So if it's positive, both facing up if it's even. If it's positive and odd, to the left you're going down, to the right you're going up. If it's even and the leading coefficient is negative, both going down. If it's odd and the leading coefficient is negative, both going opposite directions, but to the left going up and to the right going down. We can also talk about how many turning points there are in a polynomial, which is exactly how it sounds. We're talking about where we physically turn directions in our polynomials. And that might be something that I'm interested in. I also might be interested in where these x-intercepts occur, so whenever y is equal to 0. And we can find the intercepts of a polynomial the same way we've always been finding the intercepts. So we find the y-intercept by setting x equal to 0, and then we find the x-intercepts by finding y equals to 0. So here, let's go ahead and find both the x-intercepts and the y-intercept. I'm going to actually find the y-intercept first because usually that arithmetic is actually a little nicer. So that means I want to plug in 0 for x, so that ends up with 0 minus 2 times 0 plus 1 times 0 minus 4. 0 minus 2 gets us negative 2, 0 plus 1 gets us 1, 0 minus 4 gets us negative 4. Negative 2 times 1 is negative 2, times negative 4 is positive 8. So I know I have a y-intercept at 0, 8. For our x-intercept, this is where we want to set y equal to 0. And thankfully, this is already pre-factored for us. So we use a very similar technique to when we were doing quadratic equations. We're still going to use the zero product property. It's just that this time I'm going to have 3 mini equations instead of just 2. Because if this overall thing is equal to 0, then one of these 3's parentheses has to be 0. So I can undo subtracting 2 by adding 2. X could be 2. Undo adding 1 by subtracting 1. X could be negative 1. Undo subtracting 4 by adding 4. X could be 4. So it could be that my x-intercepts are at 2, 0. I have another one at negative 1, 0, another one at 4, 0. And those are all the intercepts of this polynomial. We can also predict the most number of turning points it'll have. So if we have a polynomial of some degree, it'll have at most that many x-intercepts and that minus 1 turning points. And what we mean by that is, let's take this example. So here, this guy has degree 10, because that is that leading term's power. So I don't know exactly how this looks, but in theory, I could factor this out to have 10 individual parentheses, all with different things the x's plus or minusing, for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x-intercepts. Because he is even and positive, I know the end behavior has to look roughly like this. So in theory, I could, let's say I was just weaving through each of these x-intercepts exactly once. This might be, for example, what that graph looks like. And if that's the case, let's count how many turning points I have. I would have 1, 2, 3, 4, 5, 6, 7, 8, 9 turning points. And that is the degree minus 1 to give us 9 turning points. So in particular here, we know that the maximum number of x-intercepts would be 10, because that is equal to degree. And the maximum number of turning points It might have fewer than this, but the maximum number of turning points in theory would be 9. Of course, we don't always give this to you pre-factored, so you may have to factor it yourself. And in particular, factoring by grouping will be your friend, or use substitution in order to find the factors of this polynomial. So let's take a look at what that would look like. If you have 3 terms, hopefully if you're going to be able to solve this by factoring, you want to first maybe pull out a greatest common factor. Then you want to look at maybe if use substitution works. And if neither of these work, and you've only got 3 terms, then we're going to go over in the following sections how there are additional ways that you could find the remaining zeros. But for now, these are kind of the main ways we know. If you have 4 terms, I would also check if you can go ahead and factor by grouping. Those are really the methods we want to use here. So let's take a look at this first one. So to find the x-intercepts, we set y equal to 0 first of all. Then we want to ask ourselves, does this guy have a greatest common factor? In this case, he does. And what is that greatest common factor? That would be x squared. So I can pull out an x squared. X to the 6th divided by x squared leaves me with x to the 4th. Negative 3x to the 4th divided by x squared leaves me with negative 3x squared. Positive 2x squared divided by x squared leaves me with positive 2. Then I would want to check if use substitution works. So I check if that works if this power times 2 gives me this power, and 2 times 2 does indeed give me 4. So I can let u equal x squared. That means u squared would be x squared all squared, which is x to the 4th. So let's rewrite this in terms of u. So I have 0 is equal to, and since this leading term also happens to be x squared, I'm going to just even go ahead and rewrite him in terms of u. You also could leave him as an x as well. So we have u times u squared minus 3u plus 2. All I did was replace my x squareds with u's and replace the x to the 4th with u squared. Now I want to solve this in terms of u. So let's go ahead and factor this parenthesis. Since the leading coefficient on the u squared is 1, I can jump straight to my parentheses. Still have that leading u out front. And I want to ask myself what's going to multiply to positive 2 and add to negative 3. And that should be u minus 2 and u minus 1, because negative 2 times negative 1 is positive 2. Negative 2 plus negative 1 is negative 3. Now I'm going to set up all 3 of my mini equations here. I could have u is equal to 0. That still applies. I could have u minus 2 is equal to 0. And I could have u minus 1 is equal to 0. Now you might be saying, oh, in the past I kind of always ignored this thing out front. That was because typically in the past when I pulled out a greatest common factor, it was oftentimes just a plain constant. So if I set something like 2 equals 0, that doesn't make sense. But now it's actually a variable, so I'm okay to set that equal to 0. Now I can solve each of these in terms of u. The first one's already solved in terms of u. I can solve the second one in terms of u by undoing subtracting 2 by adding 2. And I can undo subtracting 1 by adding 1. And now I can re-replace u with x squared, because that's what he's actually equal to. So I have x squared could be 0, x squared is 2, or x squared is 1. And now that I just have x squared equals number for all of these, what's my nicest way to continue to solve for x squared? I want to undo the square with a plus or minus square root. I'm actually going to rewrite those last ones so it's a little bit clearer that I'm doing a plus or minus square root on those with a little bit more room to it. So we have x squared is equal to plus or minus the square root of 2. X squared is equal plus or minus square root of 1. Plus or minus the square root of 0 just leaves you with x equals 0, because 0 doesn't have a sign. Square root of 2 doesn't simplify, so I just have square root of 2 and negative square root of 2. And square root of 1 is 1. So I just figured out all my x-intercepts are at 0, 0, square root of 2, 0, negative square root of 2, 0, 1, 0, and negative 1, 0. And those are all my x-intercepts. And you might be noticing, even though the power was 6, I didn't literally have 6. I could have had at most 6, but it's okay if some of them appear twice. In particular here, 0 appeared twice. For this next one, really the only way I can factor something with 4 terms is factoring by grouping. So let's see if factoring by grouping works. For this first group, what's their greatest common factor? That would be x squared. And let's think about what's left in parentheses. Well, x cubed divided by x squared leaves us with x. Negative 5x squared divided by x squared leaves us with negative 5. That almost exactly matches this next term, but just the sign is flip-flopped, so I should probably predict that I'm going to pull out a negative 1. Negative x divided by negative 1 leaves us with positive x. Positive 5 divided by negative 1 leaves us with negative 5. Now both of those match. Of course, I had set this equal to 0 because I'm solving for x-intercepts. So we have one parenthesis of what's the same, x minus 5, another parenthesis of what's different, x squared minus 1. X squared minus 1 factors further, because in particular here there's secretly a plus 0x in the middle, so I'm asking myself what multiplies to negative 1 and adds to 0x. Negative 1 and positive 1 multiply to negative 1 and add to 0. And now I can set up all 3 of my mini equations. So I have either x minus 5 is 0, x minus 1 is 0, or x plus 1 is 0. Undo subtracting 5 by adding 5 on both sides, x is 5. Undo subtracting 1 by adding 1 on both sides, x is 1. Undo adding 1 by subtracting 1 on both sides, x is negative 1. So 5, 0, 1, 0, and negative 1, 0 are all 3 of my x-intercepts. So this idea that we had before where like the 0 appeared kind of explicitly twice because it was both solutions to the x squared, that actually has a special name for it, and that's known as the multiplicity of a 0. So anytime I basically factor and I have that particular 0 happen more than once, that's considered his multiplicity. So let's just identify that here. So first of all, what would my zeros be? Well, I would have a mini equation of x plus 3 is 0, so x would end up being negative 3 when I subtract 3 from both sides. X minus 2 is 0, so x is positive 2 when I add 2 to both sides. And x plus 1 is 0, so x is equal to negative 1 when I subtract 1 from both sides. So I've got 3 zeros here. 1 at x is negative 3, 1 is x at 2, and 1 of x is negative 1. Now you might have noticed that I've kind of gone back and forth between this language. A 0 and an x-intercept are identical because the 0 is referring to the fact that y is 0. So they're like tomato, tomato. They are considered synonyms. You will hear both of those terms used interchangeably. So the 0 at x equals negative 3. Well, what's the secret power on his parenthesis? That's just a 1. So he has a multiplicity of 1. So that's to say that 0 appears once. For the 2, he has a power of 2 on there. So he has a multiplicity of 2. For the negative 1, he has a power of 3 on his parentheses. So he has a multiplicity of 3 for that reason. And there's a different sort of general behavior that ends up at each of those multiplicities. So when the multiplicity is 1, that ends up just going straight through the 0. Sort of like if you zoomed in on the graph right there, it would be like a straight line. For negative 1, because he has a multiplicity of 3, he also goes straight through, but sort of more at a curve, sort of like he's a mini x cubed, just right there around that 0. And when we have a multiplicity of 2, that's the most interesting because he actually just bounces off the graph like that, sort of like we have a mini quadratic right there around the 2. And that in general is actually true. So if you have a multiplicity with a power of 1, he's going to just go straight through in a straight line. If you have a multiplicity with a power of 2 or anything else even, he's going to bounce off. And the way in which he bounces off sort of reflects the overall power. So like something like x, like a power of 10, is going to bounce off much more sharply than squared. in the same way that that's kind of how those polynomials behave. Kind of knowing the nuances of that isn't really the focus of this class, but kind of in case you were curious. And then if you have a multiplicity of 3 or anything else, let me spell that. So, or anything else odd 3 or larger, that's going to go through the 0 at kind of more of a curvy shape. And that in general is true, so that's exactly what it's saying. So if it looks almost linear and goes through, it's a multiplicity of 1. If it bounces off and just touches that axis, it's going to be an even multiplicity. And if it crosses it in general, it's going to be an odd multiplicity. And in particular, if it's kind of curvy in the way it crosses, then you know it has to be bigger than or equal to 3. The difference between 1 and 3, even though I'm noting it, is not really super the emphasis of this class. Really, you should know odd goes through and in some way, and even bounces off. It just touches. That's kind of the big idea. And we can use that to work backwards and actually just write the equation of a polynomial given the graph, which is actually a very, very powerful, super cool idea, in my opinion. In order to do that, let's first just note where all the zeros are and what their potential multiplicities would be. So in particular, we have a 0 at, this first one would be -3, with a multiplicity of, let's kind of see here. So here, since it bounces off, it needs to be a multiplicity of at least 2. In theory, could be bigger, but for now, let's be conservative and let's deal with kind of the smallest possible multiplicity. We also have a 0 here at -1. So we have a 0 at -1, and it just goes through in a very linear fashion, so with a multiplicity of 1. And our last 0 is here at +4. And that goes through, but in a more curvy fashion, so with a multiplicity of 3. We also can go ahead and just write our parentheses now from here. So here we're going to kind of use a similar idea that we have in the past, that we can write a generic form of this function and then have an unknown multiplication factor. So we have y equals, we're always going to kind of represent that unknown multiplication factor with an a, although in theory it could be something else. And then let's start setting up our parentheses. For the 0 at -3, that means I need an x plus 3 here in parentheses, because at some point I must have set x plus something equal to 0 and then solved backwards and gotten that that was -3. So it must have been that I had an x plus 3 in parentheses to give us -3. And then, you know, if you don't feel super comfortable with that, that's worth actually explicitly double checking to the side, because it's just a one-step equation. If I set x plus 3 equals 0, subtract 3, I get x equals -3, just like I want. And since this multiplicity is 2, how is that going to show up? That's going to make the power on this 2. And then I want to keep on going. So I also have a 0 at -1. So that's going to be x plus 1 in parentheses with a multiplicity of 1. So just a power of 1 there. And the last one is a 0 at 4, so x minus 4 with a multiplicity of 3. Now how can I solve for this unknown multiplication factor? Well, the fact that I gave you such a specific graph means I also know other points on the graph. In particular, I would say the y-intercept is a nice other point on the graph. And where does this y-intercept occur? That's at 0, -120, because it appears halfway between -80 and -60. And -120 is 40 away from both of those. So that's the point I'm going to plug in. -120 is equal to my unknown multiplication factor. 0 is my x there, so 0 plus 3 squared. 0 plus 1, I'm not going to write the first power, but that's secretly there. 0 minus 4 cubed. Now to keep on simplifying, you want to simplify each of these parentheses first. So that's -120 is equal to a times 3 squared. 0 plus 1 is 1. But yeah, 0 minus 4 is -4 cubed. I want to actually do those exponents now that I've done the parentheses. So 3 squared is 9, 1 is just 1, negative 4 cubed is negative 64. Now I want to actually continue to simplify. So negative 120 is equal to a, 9 times 1 is just 9, times negative 64. Then at this point I could continue to do it by hand, or if I'm feeling lazy I can break out a calculator. So you want to do 9 times negative 64, that's negative 576, equals a times negative 576. And as a final step, you undo multiplication by division. That cancels out to make 1. And then you want to do 120 divided by 576, and a negative divided by a negative is a positive. And you want to be as precise as possible, so I would go with the actual fraction. That would be 5 over 24 is equal to a. So what I just figured out was that this is identical to exactly what I just predicted, but now I know that unknown multiplication factor. So y is equal to 5/24 times x plus 3 squared times x plus 1 times x minus 4 cubed. Now occasionally Alex will make you expand things out, usually with nicer numbers than this. For the purposes of a test, you can always just leave this exactly in factored form, and if Alex doesn't tell you you have to expand it out, I would leave this in factored form. There's no reason to expand this out other than an exercise in expansion. I could also give you this information in a different way. So instead of visually telling you, I could just list it out exactly where all these zeros are in their multiplicities in another point. So go ahead and pause this video and see if you can write out this polynomial yourself. So here I have y is equal to, we have an unknown multiplication factor. For 0 at 3, that would be x minus 3. For a multiplicity of 1, that's the power of 1. For x minus 2, that would be x plus 2 to result in that, with a multiplicity of 2 makes that squared. For 1, that becomes x minus 1 with a multiplicity of 3, adds a 3 here. And then for my next step, I want to actually plug in the point they gave us, which if it's a y-intercept of 6, that means I have a point at 0, 6. So I plug in 6 for y. I'm solving for my multiplication factor. 0 minus 3, I'm not going to rewrite to the first power because first power doesn't do anything. 0 plus 2 squared, 0 minus 1 cubed. Now I want to simplify those parentheses, so 6 is equal to a times negative 3. 0 plus 2 is 2. 0 minus 1 is negative 1. Then actually do those exponents, so that's a times negative 3 times 4 times negative 1. Negative 3 times 4 is negative 12. Negative 12 times negative 1 is positive 12. And then my last step is to undo multiplication with division. So a is equal to 6 over 12. I can divide both the top and the bottom by 6 to give us 1/2. So I just figured out my final equation is identical to what I just predicted, but now I know what a is. So y is equal to 1/2 x minus 3 times x plus 2 squared times x minus 1 cubed. And that is our final beautiful equation. So that is exactly how you want to, in general, solve for these polynomials, is you want to identify the x-intercepts and their multiplicity. And then you want to use some other point on the graph to solve for the stretch factor. Now on this previous one, I forgot to answer the last part. So describe its end behavior. So rather than expand this out, you can actually logic out what the degree on this polynomial is. Because in particular, at some point, I'm going to multiply 1x by 2 more x's by 3 more x's. So the highest power will be x to the 6th. And then he'll have a coefficient still of that 1/2 out front. So this I know has to be the leading term, even if I would end up doing some more work in between to find all the other terms. And if that's the leading term, what should his end behavior look like? He should look something like this. So this would be the end behavior of the polynomial because he is even and he has a positive leading coefficient. so let's talk about if this is physically possible. So your instructor's Chihuahua Eldon states that he found a degree 4 polynomial with the following zeros: 5 with a multiplicity of 2, 10 with a multiplicity of 3, -6 with a multiplicity of 4, and 0 with a multiplicity of 5. He says that's possible because there are 4 zeros for a degree 4 polynomial. Is he correct? If so, write this polynomial, and if not, explain why not. So I encourage you to pause this video and think about this problem, and then come back and we'll talk about it. So let's pretend that he is correct. Let's just kind of sketch what this polynomial would be. It would be y is some unknown stretch factor, x minus 5 squared for the multiplicity of 2, x minus 10 cubed for the multiplicity of 3, x plus 6 to the 4th for the multiplicity of 4, and x to the 5th for here, because that's really secretly x minus 0 to the 5th, but minus 0 is kind of silly, so we typically just write that as x to the 5th. And if I were to expand this out, at some point I would do 2x's times 3 more x's times 4x's times 5x's, so that would be 5, 9, 14. This has to be at least a degree 14 polynomial. Why is that a problem? Because he said he found a degree 4 polynomial, so this is not possible. If it's a degree 4 polynomial, those multiplicities better add up to 4. So your instructor's mother also has a Chihuahua, Penny, who says that she found a degree 4 polynomial whose only zero is 5. She states this is possible because she's really, really adorable. Is she correct? If so, write the polynomial, and if not, explain why not. So go ahead and pause this video and try this out. So here, if we have its only zero is 5, let's say the only zero was at x minus 3. And we wanted its only zero, only zero is 5. It gave us the only zero is 5. So only zero is 5, so that means we got an x minus 5. And it's a degree 4 polynomial, so what else would I have on here? Well, that just means I would need to make its multiplicity 4, and then that's fine, because then my highest degree would be 4. So she is correct. Maybe not because she's really, really adorable, although that's also, of course, relevant to this problem. But the biggest thing being that as long as the multiplicity is 4, we're okay. And now let's talk about some polynomial inequalities here. So in particular, what's super tempting with these polynomial inequalities is you would just be like, oh, let's set x plus 6 greater than or equal to 0, 1 minus x greater than or equal to 0, and x minus 4 greater than or equal to 0. And if you do that, you're actually going to lose out on a lot of solutions. And let's sort of think about why. If I have 3 things being multiplied together that are going to be bigger than or equal to 0, as possible, I have a positive times a positive times a positive, and that is bigger than or equal to 0. I could also have a negative times a positive. That would also be bigger than or equal to 0. Can you think of another combination as well? What about a positive times a negative times a negative? What about a negative times a positive times a negative? So there's so many different ways that this can happen. And as you can kind of quickly picture, the more and more terms we get, the harder that would be to come up with all of the different combinations where this would be true. So there's a different method we want to do instead. So in order to do this instead, I'm first going to find where we equal 0. Then we're going to place this on a number line. And then we're going to test. So let's see that in action. So in particular here, we could have x plus 6 is 0, 1 minus x is 0, and x minus 4 is 0. X plus 6 is 0 leaves us with x is equal to -6 by subtracting 6 from both sides. For this next one, I actually think the easiest way is to add x to both sides, so x could be 1. Or we could add 4 to both sides, and x could be 4. So let's go ahead and put these guys on number line. So we got -6, 1, and 4. And since this is an or equal to sign, I could equal any of these numbers, so I'm going to use closed circles. And then I'm going to actually just pick things in different regions of the number line and test it. Because what's going to be true for everything to the left of -6 will be true for anything to the left of -6 will be true for everything to the left of -6. Because if you kind of picture this inequality, he's going to be like some sort of graph that looks like this if we're talking about a degree 3 polynomial with a negative leading coefficient. So whenever I figure out something over here, it's just going to always be true. Which you could literally sort of sketch out the polynomial like I just did and figure out when he's above or below the x-axis, or I think is actually less prone to error to do what I'm about to do of find some testing points. So let's say in particular I picked out -7 as a testing point, because that was something to the left of -6. So I'm going to plug -7 into these parentheses, and I really just care about the sign. So -7 plus 6, that's a negative. 1 minus -7, that's a positive. -7 minus 4, that's a negative. So will that result be greater than or equal to 0? That result will be positive, because a negative times a positive is a negative, times another negative is a positive. So that works, and I'm going to shade him in. Let's pick another testing point. So something in between -6 and 1. I would actually say x is 0 is the nicest thing to plug in. So if I have 0 plus 6 times 1 minus 0 times 0 minus 4. So that's a positive times a positive, because that's 1 minus 0, not 6, times a negative. So a positive times a positive is a positive, times a negative is a negative. So that does not work. What about something in between 1 and 4? So I could pick, let's say 2, for example. So that would be 2 plus 6 times 1 minus 2 times 2 minus 4. And again, I care about the sign. So that's a positive times a negative times a negative. Positive times a negative is a negative, times another negative is a positive. So that ends up working. And now let's check the last region. Something like, I don't know, 5. Something beyond 4. So we have 5 plus 6 times 1 minus 5 times 5 minus 4. So that is a positive times a negative times a positive. That final result will still be negative, so that does not work. So our final answer is that I got everything less than or equal to -6 and everything in between 1 and 4. So if I'm going to write up that final answer, that would be -infinity to -6 inclusive union 1 to 4. For this next one, if you notice, the actual zeros are identical to here, so I'm going to use the same numbers on the number line. But the testing is going to look a little bit different, in particular because of this multiplicity here, and also because I'm doing a less than. And since he's a less than, am I going to use open or closed circles? All of these will be open circles. And now I want to do the same process with the testing points. So I'm even going to pick the same testing points. So let's say I picked x is -7. Then I have -7 plus 6 times 1 minus -7 all squared times -7 minus 4. -7 plus 6 is negative. Anything squared is a positive. -7 minus 4 is a negative. So a negative times a positive times a negative is a positive. Because I want less than this time, I don't want to include those numbers. Then for in between, let's pick x is 0. So now I have 0 plus 6 times 1 minus 0 squared, 0 minus 4. So in particular, that becomes a positive times a positive times a negative. Positive times a positive is a positive times a negative is a negative. So that region works this time. I do want the numbers in between -6 and 1. Now for the number in between 1 and 4, I picked x equals 2 last time, so let's just pick that again. So then we have 2 plus 6 times 1 minus 2 all squared. And of course I'm running out of room, so let me write a little bit more room here. So for that region here, x equals 2, that's 2 plus 6, 1 minus 2 all squared, 2 minus 4. 2 plus 6 is positive. Anything squared is also positive. 2 minus 4 is negative. So now a positive times a negative is going to be a negative. So this region actually also works for that reason. Now let's check the last region. So before we picked x equals 5, so let's pick that again. So then we have 5 plus 6 times 1 minus 5 all squared. I'm actually going to make myself some more room here. So we have 5 plus 6 times 1 minus 5 all squared times 5 minus 4. So 5 plus 6 is a positive. Anything squared is a positive. 5 minus 4 is a positive. So now I have a positive times a positive times a positive. That's still positive. Those are not the numbers I want because I want less than 0. So our final answer, according to this number line, is going to be that I go from -6 to 1, but parenthesis because I don't want to equal 0 itself, and then from 1 to 4. And I mostly did this answer to illustrate that a lot of times when nothing is being squared or anything like that, you do end up with this alternating pattern. But be careful that as soon as I introduce multiplicity, that might not be true anymore. So in short, the way you always do these is you want to rearrange this so that it's greater than or equal to, less than or equal to, or greater than or equal to, or less than or greater than 0. Find all the zeros and then do your testing regions on your number line. So let's practice that for these. So this one hasn't been rearranged so that one side is 0 yet. So in particular, I'm going to kind of keep my right-hand side 0 because I'm used to reading inequalities left to right. So I'm going to get rid of adding 9x and subtracting 9 by subtracting 9x and adding 9. Make 0, make 0. I'm just rearranging where these are because none of those are like terms. And now this isn't pre-factored, so I have to check if factoring by grouping is going to work. So let's try to do that. So between x cubed and x squared, what's their greatest common factor? That would be x squared. Let's think about what's left in parentheses. X cubed divided by x squared leaves me with x. X squared divided by x squared leaves me with -1. -9x plus 9. What's their greatest common factor? You might just say 9, but be careful that I want a positive than a negative. So let's try pulling out a -9. -9x divided by -9. It's going to leave me with x. +9 divided by -9 leaves us with -1. So then we have x squared minus 9. What's the same? X minus 1. Oh, x squared minus 9. What's different? X minus 1. What's the same? And then x squared minus 9 further factors into x minus 3, x plus 3, and then we have the x minus 1 there. So now let's think about what our number line is going to look like here. So we have a 0 at 3 from that x minus 3, a 0 at -3 from that x plus 3, and a 0 at 1 from that x minus 1. And do I want open or closed circles? I want open circles on all of these. And now I want to challenge you to go ahead and pause this video and do those testing points yourself. So here, something to the left of -3, let's try out x is -4. So that would be -4 minus 3 times -4 plus 3 times -4 minus 1. So that is a negative times a negative times a negative. Negative times a negative is a positive times another negative is a negative. So do I want to include or not include that region? I don't want to include that region because I want greater than 0. Let's do something in between -3 and 1. I would say x equals 0, which is in between there, is always nice to test when you can. So that becomes 0 minus 3 times 0 plus 3 times 0 minus 1. So that is a negative times a positive times a negative. Negative times a positive is a negative times another negative is a positive. So that is positive. That is a region that does work. Let's try out another point. So let's say we have x is equal to 2 for the next region. So that would be 2 minus 3, 2 plus 3, 2 minus 1. 2 minus 3 is a negative. 2 plus 3 is a positive. 2 minus 1 is a positive, so I end up with a negative, times a positive is a negative, times a positive is still negative, so that does not work. For our last region, something beyond 3, let's try out x equals 4. So we have 4 minus 3 times 4 plus 3 times 4 minus 1. 4 minus 3 is a positive. 4 plus 3 is also a positive. 4 minus 1 is a positive. A positive times a positive is a positive times another positive is a positive. So that works. So for our final answer, we have everything in between -3 and 1, union everything beyond 3. This next one also needs to be rearranged. So we first rearrange him by subtracting 6x from both sides. That leaves us with x cubed plus x squared minus 6x is less than or equal to 0. Then to factor this, we want to pull out a greatest common factor first, which is x. X cubed divided by x leaves us with x squared. X squared divided by x leaves us with x. Negative 6x divided by x leaves us with negative 6. Then we want to factor what's left in parentheses. In particular, we ask ourselves what multiplies to negative 6 but adds to 1. And that would be x plus 3, x minus 2. Now we're ready to put these guys on our number line. So in particular, from the x by itself, that's just setting x equal to 0. So that's a 0. For the x plus 3, that's negative 3. For the x plus 2, that would be 2. And since we have a less than or equal to sign, this time we're going to do shaded circles for each one. Go ahead and pause this video and try those testing regions yourself. So let's go ahead and try the testing regions on this number line. So something to the left of negative 3 would be negative 4. So that would be negative 4 times negative 4 plus 3 times negative 4 minus 2, plugging into here. So that ends up being negative 4 is still negative. Negative 4 plus 3 is a negative. Negative 4 minus 2 is a negative. A negative times a negative times a negative. Negative times a negative is a positive times another negative is negative. So since this is negative, do we want to include that? We do, because it's a less than or equal to sign. Now let's check something in between negative 3 and 0. Let's say x is equal to negative 1. So that'd be negative 1 times negative 1 plus 3 times negative 1 minus 2. That gives us a negative times a positive times a negative. Negative times a positive is a negative times another negative is a positive. So that is positive. We do not want to include that region because we want just negative numbers according to that inequality symbol. Now let's try something in between 0 and 2. Let's say x is positive 1. That would be positive 1 times 1 plus 3 times 1 minus 2. So that would be a positive times a negative. Positive times a positive gives us a positive. Times a negative gives us a negative. So we do want to include numbers in between 0 and 2. For the last one, something that is beyond 2, let's try x equals 3. So that would be 3 times 1 plus 3 times 3 minus 2. 3 is positive, 1 plus 3 is positive, 3 plus 2 is positive. Positive times a positive is still positive. We don't want to include that region. So our final answer ends up being negative infinity to negative 3, bracket, union, bracket, 0 to 2, bracket. And that would be your final answer. As always, please check out your textbook if you want to see even more examples and ask your professor as well if you want some more help. For all of these polynomial inequalities, if you felt really comfortable instead knowing how that end behavior looks and how all those multiplicities look, that is a completely valid way to do this as well. We emphasize it this way because it has historically been less prone to error for folks that are doing this entirely algebraically, but you can do this with whatever method you want as long as you actually do show your work. Or if the directions say by doing testing points, then you have to do it this method. So kind of double check with your professor on what they prefer.